Hello, in this video I'm going to talk about neutron stars and a subset of neutron stars called pulsars. So let's remind ourselves about how neutron stars are formed, because I went through this in the life cycle of stars video. And remember, we were dividing stars up into categories based on their initial mass. And this allowed us to set up different life cycles, different paths that stars take through their lives and their evolution, and the different endpoints that they reach. And neutron stars are one endpoint of one category of star. So let's just remind ourselves of all of that. If we got very low mass stars that start off less than half of the mass of the sun, then these are our red dwarfs, our brown dwarfs, very slow conversion of hydrogen to helium, so protons to alpha particles because it's all ionized. The lifespan of these stars is billions and billions of years, longer than the current age of the universe. So we've never actually seen the endpoint of one of these stars, so we have to guess. But essentially, these are just doing slow conversion through fusion of hydrogen and helium, and then they just fizzle out at the end. Then we've got the intermediate mass stars, your regular main sequence stars, including the sun. So this will be half to 10 solar masses. These stars go through hydrogen to helium, bit of helium converting into carbon, oxygen, end up with a planetary nebula forming for a short amount of time. You'll get to see a planetary nebula, and the central star, the end point, then becomes a white dwarf. So this is where we've got a white dwarf, and it stops at white dwarf stage because the gravitational force inwards is stopped. The collapse due to gravity is stopped by electron degeneracy pressure. So that is what is sustaining a white dwarf. It's that electron degeneracy pressure. Now, if you've got a higher mass star to start off with, then these are the ones that are going to go supernova. So we're talking 10 to 25 solar masses. We'll get supernova event. We'll get gravitational collapse, and the force due to gravity is great enough to overcome the electron degeneracy pressure. So it will collapse beyond the white dwarf. It will go to a neutron star, and that neutron star is then being held up by neutron degeneracy pressure. So again, we're getting into our quantum mechanics with these degeneracy pressures. If you've got a star which is greater than 25 solar masses, the gravitational collapse just continues and you end up getting a black hole. So that's a sort of high level overview of these endpoints of different stars. So for neutron star formation, we're looking here at supergiants in the 10 to 25 solar mass range. So remember, a giant, you get giants when they expand out. These will become giants. Remember on our Hertzsprung-Russell diagram, when you've got main sequence and you've got that branch that comes off the main sequence. So as these main sequence stars age and get towards the end of their lives, they expand and move off this branch to where the giants live. Whereas the supergiants, if you remember, would a population at the top of the HR diagram with high luminosity, even if they got low temperature. So you can have your red supergiants at one end, your blue supergiants at the other. So yeah, low temperature to high temperature, but they've still got the high luminosity because of the large size of the star. Right, so that's where these neutron stars are coming from, is the collapsed core of a supergiant that isn't large enough to collapse down to a black hole. So we've got very high density in these neutron stars. We've managed to squeeze the electrons mostly out of the matter in the star. So when we've got white dwarf, we've got electrons, protons, neutrons. When we get to neutron star, most of the electrons and protons have combined into neutrons. So we don't have much left apart from neutrons. It's not 100% neutrons in there, but it's getting towards it. And think back to our particle physics. If we're combining these electrons and these protons and we're producing neutrons, again, we've got quark changes here. This is going to involve the weak interaction because, think what's happening with our quarks. We've gone here up, up, down to an up, down, down for our quarks. So if we've got a change in flavor, we got a weak interaction, which means we are going to get loads of neutrinos being released. So this collapse from white dwarf down to neutron star, epic levels of neutrinos are coming out of the core of this star as it collapses down to neutron star. Of course, we got a little more actually, while I think of it, than just neutron degeneracy pressure holding up the neutron star. Because think again, going back to our particle physics, of the strong nuclear force. And you've got that sort of profile. We drew this out, didn't we? Where you've got this attractive part of the nuclear force, which is what's holding together nuclei of atoms. But if you get too close, it gets repulsive. So this is another thing which is going to be supporting a neutron star against further gravitational collapse, that you're going to have repulsive, strong nuclear forces at very, very short range. When you're getting these neutrons crazily close together, this is already, for the attractive part of the strong nuclear force, we're already getting down to atomic nucleus size, that sort of separation. To get down to the repulsive bit, you're really pushing these neutrons together. But that's how much matter you've got there, how much mass there is in such a small volume. And these densities are crazy. We're talking about getting, if you take something like the Earth, the Earth is big. You think of the radius of the Earth, say 6,400 kilometers, something like that. You're talking about shrinking that down to less than a centimeter or something like that. It's just so tiny. The density is nuts. And again, this comes back to our particle physics of thinking how much of atoms are just empty. You've got the nucleus and then just so much space around it inside an atom. And this is just removing all of that space and just packing all of the nuclei. Well, they're just neutrons now, but it's packing them all right up against each other. So you're squeezing all of that space out of the neutron star. Now, neutron stars, they don't produce any more energy. You haven't got any more fusion going on here, but they're still very, very hot and they're just cooling over time. These are the cores of supergiants, so they were very hot, and they might be starting at 10 million Kelvin or something like that by the time you've produced the neutron star, and then they're just going to cool over time. So this is 10 million Kelvin compared to the surface of the sun, where you're looking at under 6,000. So massive difference in the temperature there. So there's a lot of energy there. They're still super hot. And another part of the energy is how quickly they're rotating. Think of what's happening here for conservation of angular momentum. If you've got a supergiant which is rotating, and then you start shrinking this down, it starts collapsing under gravity, then conservation of angular momentum means they are going to be spinning faster and faster and faster. This is the equivalent of the ice skater doing a spin on the ice, where they got their arms outstretched and they're spinning fairly slowly, and then they pull their arms in and they go into a super tight, super fast spin where they're just going crazily quickly. Well, you've got this magnified up to the max here when you're shrinking down something as big as a supergiant to something as small as a neutron star. You're getting a massive increase in the speed of rotation. So you can be getting several hundred rotations per second in neutron stars just through this conservation of angular momentum. And this can be accelerated as well with neutron stars. Think of what I was saying in the binary star video about how many stars are in binary systems. So if you've got one star has gone supernova, it's collapsed down to neutron star, well, it's very dense, it's got a strong gravitational pull, it might be accreting more matter off of its binary companion, and it can just start spinning faster and faster and faster and start emitting X-rays as well. This is moving into pulsar territory. So you can get these things that are called millisecond pulsars. So you've got a lot of matter falling onto something very hot, being accelerated in this circular motion through the rapidly spinning neutron star. So you've got this rapid acceleration of ionized matter, so accelerated charged particles. That means we're getting a lot of electromagnetic radiation being emitted. And this is then when you're getting millisecond pulsars, which are releasing loads of X-rays, high energy electromagnetic radiation, because of this acceleration, high acceleration of ionized particles. So yeah, that brings in nicely then to what a pulsar is. I mean, I've pretty much already said it. So pulsars, these are highly magnetized neutron stars emitting electromagnetic radiation, and they emit from the poles. You know what it's like. We've got the Earth's magnetic field, where you get the magnetic north and south pole. Always looks like an elephant whenever I draw this, but yeah, you've got these magnetic field lines coming out. You've got something similar going on in neutron stars with a much stronger electromagnetic field. And these electromagnetic rays, radiation that we're getting, these X-rays and such like, as I say, one way you can get them is from matter being accreted onto the neutron star, but you can also get these magnetic fields forming inside the neutron star. They're not 100% neutron. You've still got some protons and electrons there. So again, we've got these highly accelerated, because they're spinning around in circles. We've got this centripetal acceleration going towards the center of the neutron star. So we've got accelerated charges. This is then going to produce electromagnetic effects. So you've got different ways that these X-rays can get emitted. And we end up seeing pulses of these, depending on the orientation of the neutron star and its axis that it's spinning on. And then we can get pulses of X-rays directed towards the Earth. And these were first discovered in 1967. Jocelyn Bell, the Northern Irish astronomer and astrophysicist, she was actually a research student at the time. So yeah, she was still a student when she discovered the first pulsar, and a second one was found soon after, ending the speculation that maybe it was bad readings, maybe it was weird measurements or whatever, maybe it was aliens. Who knows? There's always the chance that some kind of synchronized signal coming from outer space is going to be deliberately constructed. Maybe it was an alien signal, but no, it turns out they found a number of these quite quickly, and it was clear that it was a new type of object. So yeah, this was what was leading into then them being termed pulsars, understanding how they behave, how they form. People were still putting together the life cycle of stars at this point. This is relatively new science going on here. Yeah, I mean, the magnetic fields, as it is with these ultra strong magnetic fields and very high temperatures, they're not that well understood. They haven't been modeled particularly accurately or convincingly yet, because there's still so much which is unknown about how these magnetic fields work. I mean, look at how little is understood comparatively about the magnetic field of the sun, and how that is transferring energy into the corona and those very high temperatures that we see beyond the surface of the sun. So we've got a similar problem with pulsars. These are way beyond the sort of magnetic fields that we're creating on Earth in the lab and such like. So there's a lot of modelling that's going on, trying to understand how pulsars, how they work, how they create these exceptionally strong magnetic fields, because they really are just off the charts when it comes to magnetic field strength. So yeah, there's a lot of work in this area. There's a lot of new discoveries to be made, because they're just such extreme objects. And whenever we get extreme objects, you're really pushing the limits of what we understand in science. And that's certainly going on with neutron stars and pulsars. So there you go. That's an overview of that. I'll leave you with one famous neutron star, the M1, first one in the Messier catalogue. This is the Crab Nebula. So it can, like with all of these objects, or so many of these objects, it's called a nebula. It's not a nebula. It's a supernova remnant. This was a supernova that went off in 1054. So we're going back over well, nearly 1,000 years here. And so pre-Norman conquest and William the Conqueror and all of that. And yeah, there was a very bright supernova that went off, and it's left this remnant. So in the middle of the Crab Nebula, to say it's not a nebula, but in the middle of it, you've got a neutron star, which is the leftover part of the star that went supernova. So that's the one that everyone thinks of. If you say to someone, name a supernova remnant, name a neutron star, that's the one that they're probably going to pick out 99 times out of 100, unless they're a specialist. So there you go, neutron stars.